Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Art. In this tutorial video, we'll go through this AQA topical series. This is about reaction mechanism in organic chemistry. This is for the 16 to 18 years old A-level contents, which are also suitable for any students doing this A-level curriculum or a similar kind of advanced chemistry curriculum all around the world. In this first question, we have this question which is asking us which of the following is basically the correct mechanism. So you need to outline the correct step-by-step process. This is the formation of the alkene. As you could see, you have a carbon-carbon double bond alkene, and you obtain this from the haloalkane. You can see the two bromo and then the alkane there. So this is basically haloalkane going to alkene. We are talking about elimination. What exactly are we eliminating? We are eliminating the HBr, which of course we would use things like NaOH in alcohol. So if I draw out the skeletal formula, this is like 1, 2, 3, and 4. We have a but2 so my double bond is between the 2 and the 3 there, and I have another methyl group there. So I'm forming that alkene, but I'm forming it from these 2 bromo 3 methyl butane. So 2 bromo 3 methyl butane. So I guess I can draw my bromo there and my methyl there so that you can see exactly what I'm talking about here. Okay, so that is 2 methyl butane, that is 2 bromo 3 methyl butane there. So what we can talk about here is we're gonna use NaOH, and this NaOH or KOH is in ethanol. So the NaOH or the KOH in ethanol is acting as a base, and therefore what I'll do is acid-base reaction here, where I will get out NaBr but also get H2O. Instead of getting HBr, which that's why I put in an inverted comma, okay, instead of eliminating just HBr, you are using this as a base, therefore you form salt and water for these balance equations. The first thing is the OH minus, we'll use it as a base. So all of these except this one here, the OH minus should be acting as a base, so it should be looking at protons and not on the carbon because it's not acting as a nucleophile. Now to the other one, we are looking on the adjacent hydrogen because this is the carbon. This is the carbon with the halogen. So really we are looking on the adjacent hydrogen, the hydrogen on the adjacent carbon, which could be there, which could also be there on the CH3 there. So I know I want to get a but2 if I eliminate from this carbon 1 here. So my double will be between 1 and 2. I'll get the but1 instead of the but2. So it cannot be this because it will give but1 What I'm saying is the alkyl will be at position 1 at the end there, so cannot be that. So now we're left between B and C. What is it between B and C that we're looking at? Okay, this one is the step that is wrong because you're supposed to take the hydrogen from the adjacent carbon, whereas this is carbon with the halogen. You should be taking it either from here or from here. So C is definitely wrong. In the end, you're left with option B, which is the only correct answer there because it's adjacent hydrogen. It's the one that will give you your double bond between carbon number 2 and carbon number 3 of the straight chain to give us the product. Draw and see for yourself, yeah? In this second question, we're talking about uses of halogenal alkanes despite the environmental concerns. So this is bromoalkanes, it's used in fire extinguisher. So we're talking about free radical substitution reaction. This is a case study. It is similar. Similar means you know your case study, you are just applying to a different case study here. In the initiation step, we're going to form the radicals. So this is reaction with Br2. So that is Br2 becoming bromine radical plus bromine radical, which is 2 bromine radicals. We need UV light to do initiation. There are 2 propagation steps because you want to show the formation of the product of the substitution product. So you don't get to the substitution product in one propagation step. So the Br dot, the radical, plus your molecule. The radical is going to take away the hydrogen such that you get HBr, but you will then get CF3 radical. Now the CF3 radical is going to react with another molecule of bromine, and this will give you your substitution product. and it will kick out the other radical. So it doesn't matter whether you put the radical on the left or on the right, it's the same thing. And what happens with propagation is you have one radical on the left, you have one radical on the right. Same thing with propagation, one radical on the left, another radical on the right. Termination is basically when the radicals recombined. So radicals recombined in your termination step. So what happened there is we got to show the formation of the products. So termination could come in various stages, but I want to show the formation of the product. So I have CBrF3, or I could write BrCF3, doesn't matter how I write it. But I know it's a combination of a bromine radical with a CF3 radical. So radical and radical recombined in order to give me the final molecule, which is not a radical there. Step 1 condition necessary, so that is your UV light or your ultraviolet light, which is required for the initiation step. We just need to break the covalent bond with the help of the UV light there. In part B, we're talking about display formula. They even bolded it for you. To complete the following question, to show how the CBrF3 may produce bromine atoms. We got to draw the display formula. So basically, if I break off the CBr bond, what else am I left with? I'm left with CF, CF, and CF. I have a radical. That is because the energy of the CF is stronger than the energy required to break the CBr, because fluorine is smaller atom, smaller size, lesser filled electron shell, and therefore you can talk about shorter covalent bond. That means the localized shared pair of electrons in the covalent bond is closer to the two nuclei, therefore more attracted. Therefore, we talk about stronger covalent bond, therefore require more energy to break. Therefore, you will break the weaker covalent bond to do the free radical substitution there. In the upper atmosphere, you are more likely to produce bromine atoms rather than chlorine atoms. That was exactly what I said there. So the CCl bond is stronger than CBr. Yes, we talked about CF just now, but it's the same concept. So chlorine is smaller size than bromine. So we can talk about chlorine has smaller size than bromine. Chlorine atom is smaller in size, and this is due to lesser filled electron shells. As you know, period number tells you how many shells get occupied. So therefore, CCl bond is shorter. So that means your covalent bond will be stronger, because your localized shared pair of electron is going to be seeing or much closer to your two neighboring nuclei to give you your definition of covalent bond there. In part 3, we have this catalysis. So we're going to talk about catalysis. All these, the catalyst is in the same state. They are in the upper atmosphere. They are in the same phase or the same state as the reactant. This is part of rate of reaction topic. This is called homogeneous catalysis. Homogeneous, homo means the same. Homogeneous catalyst means they are in the same phase. The catalyst is in the same state as your reactants. These are atmospheric chemistry, to be honest. So how these two decomposition equations show that is behaving as a catalyst. So a catalyst is regenerated. So you got to show that the catalyst gets regenerated, because a catalyst is not used up. It can get involved in the reaction. That is how it provides alternative reaction pathway with a new low activation energy, but it's not used up at all. So the first thing is the ozone will react with a Br dot, just like with a Cl dot in your case study, and I'll get BrO dot, is that correct? Yeah, as well as O2 molecule. So this is a molecule, this is an element, a molecule, and it has no charge, it has no radical, it's not a radical, it is this one that is a radical species here. So what happened is that was the first O3 molecule. I involved two O3 molecule. So the second O3 will react with BrO dot, and I will also get back my Br dot. But after having formed the Br dot, that O3 and O4, which it doesn't exist, but I will produce two of the O2 molecule. So when I add equation 1 and equation 2, so you will see the left side added with the left side. What I get is O3 plus O3 plus Br dot plus BrO dot and that's going to give me my right side because adding the left equal to the right being added together. So what I get is BRO dot, oops, probably should write exactly how it appears on the right side, and I will get plus O2 plus BR dot plus 2O2. I'm going to team up the stuff that are appearing on both sides. So the BR dot appearing once, the BR dot appearing once on the right side as well. Now we can look at the BRO dot and the BRO dot. They also appear once and twice. 2O3, because this comes down to 2O3. And what does this form? So this will form, well, you have got the O2 and 2O2. That's going to give you 3O2. And you will see that, number one, there are two things I can comment here. The BR dot does not appear in the net equation because it's not a reactant. It is not a reactant. But what exactly they are looking for in your explanation is that you reform the BR dot in the end. You reform the BR dot in the second equation. That is essentially what they are looking for the correct explanation. You will get away with that. So in the second step, in your explanation, in the second step, the BR dot was regenerated. Therefore, it's not used up. Therefore, not used up, i.e. as a catalyst, is not used up at all. Okay, so you do not really need to show the adding equation 1 and 2. I would say that, in terms of whatever they would like to see as explanation, is definitely the regeneration of the catalyst in step 2, having reacted the BR dot to form this intermediate, and therefore you will show the regeneration of the catalyst there. And that's it really for these 10 marks questions. I think that's it really for these short tutorials on just a reaction mechanism. So far we've done free radical substitution, and earlier we see elimination mechanism. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. And follow me at ptet.chemistry. There's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. And to get in touch at country code +673. And then the number is 8656158. So get in touch. You can also get the number from the video descriptions and for private tutoring for AQA or any other examination board. Thank you for watching again. I'll see you in the next tutorial video.